Welcome everybody to our seminar today. So Guy David is going to talk about quantitative decompositions of Lipschitz mappings.
Yeah, so thanks a lot to Camilo and Sylvia for organizing this. I wish it was in person, but well, welcome to Indiana. You can hear the bell tower outside my office, but hopefully that will stop. So this talk is about some recent joint work by myself and Ranan Shul from Stony Brook, and there will be a kind of a bit of a survey, and then hopefully by the end we'll get to the new results and some proofs. Okay, so I'm going to start kind of very broadly, and there's a kind of broad question here, which is you have a one Lipschitz map, so a map that does not expand distances between two metric spaces. And you have a parameter, a positive parameter alpha, which is a kind of error bound. And what you would like to do is to decompose the domain of this mapping, so the X, the domain of this mapping, into a finite number of pieces, that's this E1, E2, E3, etc., plus an extra set G, which I think of as a kind of garbage or error set. And you want this decomposition to have certain properties. Okay, so I'm going to be very vague at the beginning, and we'll try to make these more precise. So the first property is that you would like the restriction of the mapping to each of these finitely many pieces to be simple, so simpler than a generic one Lipschitz mapping. What exactly simple means, we're going to discuss. Okay. You would like the size of this garbage set to be controlled by this parameter alpha, so as small as you want. Okay, so that's a decomposition. And the word quantitative is this third condition, which is how simple the mapping is and how many pieces you need in this decomposition should really depend only on this parameter alpha and, okay, maybe on some ambient dimensions, but not on the particular mapping F. You would like to be able to make some guarantees independent of this particular mapping, okay? So that's what I mean by a quantitative decomposition. You decompose the domain so that your map is restricted to be simpler on each piece with a garbage set of some arbitrarily small size. Okay. So let me try to illustrate this in a specific example, which is non-quantitative. So it's a decomposition, but it doesn't have this third condition. This is a kind of classical lemma. I attribute it to Federer, but I'm not sure if that's correct or not. It's just in Federer's book. So this is, you have a Lipschitz map from one Euclidean space to another. Then you can find, I guess I should say, countably many sets in the domain, RD, such that the restriction of your mapping to each of these sets is a bi-Lipschitz embedding, a bi-Lipschitz homeomorphism onto its image. Okay, so it preserves distances up to some constant factor. And the remaining stuff has small image in the d-dimensional Hausdorff measure. Okay, so I mean, this RD minus the union of your sets is this garbage set that I call G, and the d-dimensional Hausdorff measure of the image of that stuff is 0. So that's what I mean by the size of the garbage set is small. And item 1 says that the mapping on each piece is simpler. It's an embedding, right? It's in a quantitative way. Okay. So, all right. So here we're measuring size of garbage set by d-dimensional Hausdorff measure of the image. What we don't get in this is any quantitative statement, right? Because we don't have any control on the number of Lipschitz, on the number of these sets EI, or on what the bi-Lipschitz constant is. I should maybe say a few words on how you prove this. It's a kind of not too difficult consequence of Rademacher's theorem. So Rademacher's theorem says this Lipschitz map F is differentiable almost everywhere. Okay, and the idea is to take these sets EI to be sets on which the derivative is kind of approximately constant, right? So the derivative is an L infinity function. And by some measure theory, you can find sets where it's approximately constant, and those are the kind of right sets to choose. So for Federer, this fact is kind of a lemma that he uses to prove things like the co-area and area formula for Lipschitz. And so let me reiterate the main point of this is that this is a decomposition theorem which is not quantitative. You don't know how many pieces there are probably infinitely many. And you don't know the bi-Lipschitz constant on each piece. And even if you do, it probably depends on the particular mapping and decays to 0. All right. So there are some quantitative refinements, so quantitative improvements of this Federer lemma. Took much longer and need a lot more work. So these started with David, so this David is not me. These started with work of David and Jones in the 80s. They were thinking about problems involving singular integrals and uniform rectifiability and things like that. And as part of that work, they were interested in quantitative versions of this theorem. And I'm not going to state their theorems. What I'm going to state is a newer result given by Renan Schul, which kind of generalizes their work. And oops, I'm having some problems with my pen here. Let me try to exit out for a second, reshare this, reopen this. Sorry about that. Okay, I think I'm back. Yeah, am I back? Can people see the screen?
Yes.
Okay.
Yes. Everything's fine. And with no lines now.
Yeah. Sorry about that.
No problem.
So right. So there's a quantitative refinement of this that was given by David and Jones in the 80s, and then further improved by Renan Schul. So the result goes like this. You have a one Lipschitz map from Euclidean space into an arbitrary metric space. Okay, and so I restrict the map to just the unit cube. It's a little bit easier. So you have a map from the unit cube of d-dimensional space into some arbitrary metric space, and you have this parameter alpha, which is supposed to be your kind of error bound. Then you can decompose the whole domain into a controlled number of pieces, a finite number of pieces plus a garbage set, where the restriction of your map to each piece is L by Lipschitz, so it preserves distances up to some constant L. Okay. The Hausdorff content of the image of the garbage set is small, so I'll say a little bit more about Hausdorff content in a second. Okay, so that's the size of the garbage set is small. And most importantly, it has this quantitative condition. So this by Lipschitz constant L, how simple the mapping is, okay? And the number of pieces in the decomposition, this number n, really depend only on alpha, your error bound, how small you wanted the garbage set to be, and on this dimension d, but it does not depend on the particular map f or even the particular metric space that you map it. So this is a quantitative improvement of this lemma of Federer that I showed you earlier. I should say a little bit about this Hausdorff content. So this is just the infimum of the sum of diameters of balls to the power d that cover your set. Right? And the difference between this and the Hausdorff measure is that you don't require the balls to be small. So it's a way of measuring size. It's not a measure. It's a content. But that turns out to be the right condition. So for this kind of problem. Okay. So you have a quantitative decomposition of your mapping to pieces on which it's by Lipschitz, plus a garbage set which has small content in the image. Of course, you can't expect the content in the domain to be small because your mapping may be constant on a large piece of the domain, but this is kind of the best you can do. Okay. So I want to go a little bit on a tangent here for a moment. This is not the main subject of the talk, but it's a very interesting subject in its own right, which is this result of Schul is extremely general. I mean, in terms of the target, you can map into any metric space you want, but you have to start in Euclidean space. Your domain has to be a Euclidean domain. There are interesting questions, I mean, results and questions about what happens for mappings between more general metric spaces, where the domain is a more general metric space. So if you know about Carnot groups, this is a kind of well-studied class of metric spaces that kind of are generalizations of Euclidean space. And there are results like this for mappings between Carnot groups, some positive results like this. There are also some positive results in a kind of even more general setting for mappings between certain topological manifolds with certain properties. I don't want to get into the weeds on this, but there are results in this vein. But kind of interestingly, there are also a lot of counterexamples. So there are also a lot of situations, if you're talking about general metric spaces, where these results completely fail to hold. So there are results of there are examples of David-Sems where you have a Lipschitz map between two metric spaces. It even has extremely strong analytic properties. It preserves the measure of all sets, but it fails to have this kind of by Lipschitz decomposition. There are results of Laxo which show that a lot of common assumptions and analysis on metric spaces, for example, this Poincaré inequality and doubling and things like this, are not enough to produce these theorems in general. And there's a very interesting paper of Ladonna, Lee, and Raiola, where they show that if you have a mapping from the Heisenberg group, so it's one of these Carnot groups, to a metric space, these results can fail. So between two Carnot groups, from the Heisenberg group to another Carnot group, you have such a theorem. But from the Heisenberg group to a general metric space, you don't have such a theorem. So somehow Euclidean space is very special here. It allows you to use any target. And for more general metric spaces, there's a kind of bit of a mystery as to what's going on. But this is not the subject of this talk. So in this talk, all of the domains are going to be Euclidean. The targets are going to be metric spaces, although the results I'm going to talk about are new, even if you only care about Euclidean spaces. Okay. So the main subject of this talk now is about what happens for mappings that lower dimension. So if you think about this result of Schul that I showed you earlier, it only guarantees something if the image of the mapping actually has positive d-dimensional content, if you didn't crush all the measure to zero, right? If you did, then the theorem applies, but it's vacuous, right? So it says nothing about mappings from R3 to R2. And there's no way it could, because you cannot expect your mapping to be by Lipschitz on any large piece of the domain. If you map from R3 to R2, the dimensions don't work out right. Okay. So the main question here is, what can you say for Lipschitz mappings in this context, right? So can you decompose a Lipschitz mapping, say, from R3 to R2 into simple pieces plus an arbitrarily small garbage set? And I guess the first question before that is, what does simple mean? Because it does not mean by Lipschitz. Right? So let me just state the question again in a slightly more general way. You have a Lipschitz mapping that lowers dimension. Okay, so you have a mapping from, now I'm going to call n plus m dimensional Euclidean space to some n dimensional space, which if you like, you might as well think of as Rn, but I'm going to be a little bit more general. Okay. And again, the question we should start with is, what does simple mean here? Okay. And well, it's not too hard to answer this question. I mean, what is the simplest possible mapping from an n plus m dimensional space to an n dimensional space? It's just an orthogonal projection, right? That is the model for the simplest possible mapping, right? So in other words, if you write points of R, if you view Rn plus m as Rn cross Rm, then you would like the map to just look like the mapping that sends x, y to x, that forgets the last m coordinate. That's kind of the model for the simplest possible map. Okay. So that inspires this definition. So this is the definition of something called a Hardside set. So this is a name that comes from a paper of Azam and Schul, where they were interested in quantitative analogs of Sard's theorem. Okay. So roughly speaking, a Hardside set is a set on which your mapping looks like an orthogonal projection up to some change of coordinates. Okay. So you have a Lipschitz map. A subset of the domain is a Hardside set for this mapping if there's a globally by Lipschitz map. So this is the change of coordinates. This is G. So you have a globally by Lipschitz change of coordinates on Rn plus m, so that if you adjust your mapping by this change of coordinates, if you precompose your mapping by G inverse, then the new mapping capital F is constant on vertical planes, at least inside the set, right? So vertical planes are m-dimensional in this world, okay? And by Lipschitz on horizontal planes, so horizontal n planes, okay? So if you move up and down, the mapping stays constant. If you move in the n-dimensional transverse directions, your mapping is by Lipschitz. That's, to me, a good expression of you look like an orthogonal projection in these coordinates. So I'm going to try to illustrate with a terrible picture here. So on the right of this picture, what you see here is the original map. Right, little f. And there are some blue curves and some red curves. So in here, the picture is kind of illustrated in the n equals 1 and m equals 1 setting. Okay, so you're mapping from R2 to a one-dimensional space. And you should think of the blue, at least I intended to think of the blue as like the fibers of the mapping. The blue curves are inverse images of points. And then on the red curves, the mapping is by Lipschitz. So on each red curve, the mapping is a by Lipschitz homeomorphism. Okay. So here's what your original map looks like on the right here. And once you apply this change of coordinates G, you straighten out all of these things, right? So now your mapping is constant. The new mapping, capital F, adjusted by the change of coordinates, is constant on these vertical fibers and by Lipschitz on these red. So it's a kind of like a rank n mapping. And I tried to even draw the picture, although I'm not sure how seriously you should take this, but how accurately you should take my picture. But for example, this fiber of the mapping has two connected components. And so that means it kind of corresponds to a fiber. That means kind of two of these curves over here actually correspond to the same fiber, something like that. So after this change of coordinates, your mapping looks like an orthogonal projection. What is slightly misleading about this picture is that what I drew is some kind of open connected set, whereas in general, this Hardside set should just be some measurable set, but it's hard to draw a measurable set. Okay, so this is kind of the model of our simple mapping. Okay, so now we can ask a new question. Kind of by analogy with this result of Schul, which you can think of as basically the m equals 0 case. You can now ask, suppose you have a mapping from n plus m dimensional Euclidean space into some n dimensional metric space, which again, you can think of as Rn, if you like. Okay. And you have some alpha, some parameter. Can you decompose the domain of your mapping into a finite number of pieces plus a garbage set, where each of these pieces is a Hardside set for your mapping. So your mapping looks like an orthogonal projection on each of those pieces. The Hausdorff content of the image of the garbage set is as small as you want it. and everything is quantitative. So the number of pieces and the constants involved in all of these by Lipschitz mappings depend only on alpha and, well, there's no d, I guess that should be n and n. So that's the question, right? It's this exact analogy of Schul's result in this dimension lowering setting. And the answer to this question is no, you cannot actually do this. So there's something more subtle about this dimension lowering setting. And the reason you cannot do this is actually because of one reason is because of this old construction of Kaufmann. So Kaufmann gives a kind of amazing example of a C1, although for our purposes, Lipschitz is good enough, a C1 surjection from the unit cube in 3 dimensions to the unit square in 2 dimensions, whose derivative has rank at most 1 everywhere. Okay? And if the derivative of this mapping has rank at most 1, then it cannot have a Hardside set. So here you should think of 3 as 2 plus 1, right? So if this mapping had a Hardside set, you would expect it to have some pieces on which it looks like a projection from R3 to R2. But if the derivative has rank less than or equal to 1, it's easy to see that you cannot get a piece like that. So there can't be any Hardside pieces. On the other hand, the content of the image is positive. The content of the image is the whole unit square. So this example kind of completely destroys this naive question that was on the previous slide. And I should talk a little bit about Kaufmann's example, although I'm not going to give too many details. So first of all, we should all note that Kaufmann's example cannot be C2, right? Sard's theorem says if this mapping was C2, then the set of critical values would have 2-dimensional measure 0, but the set of critical values is everything, right? So you cannot make this example C2. Maybe I'll just say a little bit about how Kaufmann's example works. I mean, so you're trying to construct a mapping from the unit cube to the unit square, onto the unit square. And the idea is to kind of factor it through an intermediate thing. And the thing you factor it through is a tree. All right, so you pick some kind of appropriately quickly branching metric tree, okay? And the idea is it's not too hard to make a map from a cube onto this tree. And if so the tree is a 1-dimensional thing, but the set of leaves of the tree might be a thing of large Hausdorff measure, Hausdorff dimension, okay? And so if you choose this tree appropriately, you can actually map this tree onto the unit square by a Lipschitz map. Okay, so somehow the set of leaves kind of are enough to cover the whole unit square. And because this mapping factors through this 1-dimensional tree, its derivative is going to have rank at most 1. Okay? And so, I mean, another viewpoint on what's going on in Kaufmann's example is that if you look at a kind of very small cube in the domain, what happens to the cube under F? Well, it maps to something in the plane. It maps to something very close to a line, or even close to a point if the derivative is rank 0. So it has very small 2-dimensional measure. Any small cube maps to something with very small 2-dimensional measure. But the fact is there are just a lot of cubes in the domain, right? So there are, right, the number of cubes in the domain scales like radius to the power 3. And so you have enough cubes in the domain to assemble them to cover the whole unit square. That's it. Okay. So Kaufmann's example has completely destroyed our question. So we need a new question. We need a new idea. And the idea is a different way to measure the size of this garbage set. Okay. So Kaufmann's example is kind of degenerate in certain ways because it crushes many cubes. It crushes the 2-dimensional content of cubes. And we want to try to capture that. So in fact, Azam and Shul already had this in mind, and they gave the following definition. So you have a Lipschitz map into a metric space, and you have a subset of the domain. And we're going to define something called the mapping content with these parameters n and m, the mapping content of f on this subset. And it goes like this. So it's a strange definition. I'll try to explain it a little bit. So you take the infimum over all coverings of your set by dyadic cubes. Okay, so you have your set here, and you kind of cover it however you like by dyadic cubes. Okay, and then you add up the n-dimensional size of the n-dimensional content of the image of that cube times the side length of that cube to the power n. So it's a kind of thing that mixes the outputs and the target and the domain. And so this is this quantity. So you take the infimum over all coverings of your set by cubes. So this is a little bit strange. It's a little bit easier to think about what's going on in this way. So when is this quantity small? So it's small. There's kind of two ways that this quantity could be small. So one is that your set has small measure. If your set has small n plus m dimensional measure in the domain, then certainly the mapping content will be small. Okay. On the other hand, your set could have large measure on the domain, but it could be covered by cubes that are badly compressed by this function f. Okay. So you can cover your set by, if you can cover your set by a bunch of cubes whose kind of n-dimensional contents are badly compressed by the mapping. So the content of the image of that cube is much smaller than the content of the domain, which is just psi to the power n. Okay. Then this set has small mapping content. And this is exactly what happens in Kaufmanns. Okay. There's maybe one other way to view what's going on in this definition, which is to kind of think of so this is a coarse this is a kind of coarse thing. The cubes can be of any size you want. So there's a kind of infinitesimal analog. So just like there's an analog between like d-dimensional Hausdorff measure and d-dimensional Hausdorff content, right? One of them you require the balls to be small, and one of them you allow coverings by any size objects. So this is kind of the coarse world over here. There's an analog between this mapping content and an infinitesimal quantity, and that's the L1 norm of the integral of the Jacobian of the mapping, of the n-dimensional Jacobian. So the n-dimensional Jacobian of a mapping is just you take the derivative and you look at the product of the n largest singular values. And if you integrate that over this particular set A, that's kind of like the infinitesimal version of this quantity. Okay, right? If the set A has small measure, then certainly this quantity is small. On the other hand, if the set has large measure, but the mapping is kind of very compressive on that set, then that quantity is also small. So that's the idea of this mapping content. Okay. And now we can refine our question. Okay, I should say, I should explain what Azam and Shul used this result for. So Azam and Shul used this to prove a theorem. So they showed that this mapping content is exactly the right quantity to look at if you're looking to find one Hardside set for your mapping. So one piece on which your mapping looks like a projection. Okay. So they proved the following result. So assume that your target space has kind of controlled Hausdorff n measure. So controlled n-dimensional Hausdorff measure. This is what I mean when I say it's n-dimensional. Okay. then you can find one of these hard-sard sets for your mapping. You can find one of these sets where your mapping looks like a projection, if and only if this mapping content is positive. Okay? And in fact, there's a quantitative relationship. So how big the hard-sard set is that you can find is related to how big this quantity is in a controlled way. So Azam and Schul showed finding one set where your mapping looks like a projection is equivalent to this quantity being positive. And what they didn't do is give a decomposition of the mapping, right? So they found one large piece where something good happens, but what they didn't do is give a decomposition. And actually they asked explicitly in the paper, they kind of refined our previous question. So we had a previous decomposition question that was wrong because of Kaufmann's example. And so they kind of refined that question. And they asked, okay, suppose you have a mapping, a mapping from Rn plus m into an n-dimensional metric space. You have an error alpha. Can you decompose your domain into a finite number of pieces plus a garbage set on which your mapping looks like a projection on each piece? The mapping content of the garbage set is small. So you cannot replace this by the size of the image. That's what Kaufmann says. But you can ask, all right, maybe you can make the mapping content as small as you want. And everything is quantitative. So there's all these constants involved, the number of pieces in the decomposition, the by Lipschitz constants in all of these hard-sard sets depend only on the parameters and not on your specific map. So they asked this explicitly, and well, yeah, that's the main result of this talk. So the answer is yes, you can get a decomposition like this. This is kind of an improvement of this result of Azam and Schul that was on the previous slide. Okay. So I'm going to talk a little bit now about what goes into the proof of this. I'm just trying to give people a minute to maybe just digest it. So this gives you a way of decomposing an arbitrary Lipschitz mapping into a metric space. So there's kind of two steps in the proof of this. And I'm only really going to talk about, I'll mention both of them, but I'll talk more about one of them. So step one is reduces this problem. So we're looking to find hard-sard sets. We're looking to find pieces where our mapping looks like a projection. Okay? Step one is to reduce this to a different problem. Okay? So step one says, if you can do something else, then you can find hard-sard sets. Okay? And the something else is find a set on which the map f of x, y, comma, y, so the map supplemented with kind of m extra coordinates is by Lipschitz. So if you remember, the notation here is that this is a point in Rn cross Rm. So the x is in Rn, the y is in Rm. This maps into an n-dimensional space. You may think of that as Rn. And so this is also mapping into Rn cross Rn. So if you're able to add back the m missing coordinates and get a by Lipschitz map, then you can decompose further into these hard-sard sets. That's what step one says. Okay, so it reduces the problem of finding these hard-sard sets to the problem of kind of supplementing your map by a projection to get a by Lipschitz map. Okay. So, I mean, just to get some flavor of what's going on here, if you're mapping, I'm going to again draw the case where n and m are both 1. So we're mapping from kind of R2 to R. Okay. If your mapping already looks like the downward projection, so it's just f of x, y equals x, okay, then when you supplement it by y, then you get, well, just the identity map, which is a by Lipschitz map. Great, hooray. Okay. On the other hand, if your mapping happens to look like a projection in the wrong direction, if it projects onto the y-axis, then when you supplement by the last y coordinates, you get this mapping, which is not by Lipschitz. The mapping y comma y is not by Lipschitz. So somehow you have to do something else. But what this step 1 says is, if you're in the good scenario, if you're in the scenario where you can supplement by this y coordinate to get a by Lipschitz mapping, then you're essentially done. Okay. So of course, step 2 is, how do you actually decompose into pieces which admit this kind of supplement to be by Lipschitz? Okay. And we just saw in this previous example that you cannot necessarily do this as stated, because if you just are a linear projection in the wrong direction, you have already made it impossible. So the idea is you have to allow yourself some flexibility. You have to allow yourself a flexibility to kind of change coordinates. Okay. So that's what step 2 says. So step 2 says, if you're in our setting, if you have a Lipschitz map into a metric space, then you can decompose the domain into a controlled number of pieces plus a garbage set, where on each one of these pieces, there's a change of coordinates, this phi I, so that if you precompose your mapping by this change of coordinates, then supplementing by y makes it by Lipschitz. Okay. So if you kind of adjust your mapping, then it has this extra supplement to make it by Lipschitz. And the garbage set has small mapping content in the sense that I described, and everything is quantitative, only depends on alpha and n and m. Okay. So step 1 said, if you can find this sets where your mapping has a supplement, then you're in good shape. And step 2 says you can find these sets as long as you allow a kind of change of coordinates. Okay. So I'm going to talk a little bit about the proof of this in the last, however, 10 minutes of the talk. I should mention before I get into the proof that this is closely related to some ideas of David and Sem's. And this David is, again, not me, from 2000. So they were interested in also in this problem of supplementing by linear maps. They studied a certain subclass of Lipschitz mappings called regular mappings, and they kind of sketched some ideas which are very similar to the ideas that I'm going to show you. So we were not the first people to use these ideas, but it's a little bit more general. Okay. So yeah, maybe one last remark before the proof is that this step doesn't require anything about this target space Y. So this step actually says something about Kaufmanns' example. Okay. So the main engine, the main thing that goes into the proof of this result is this idea of quantitative differentiation. And this is not just, there's not just one theorem. This is kind of a very general principle that's been used in a lot of contexts. And I mean, even if you're not that interested in decomposing Lipschitz maps, so it's the main subject of this talk, this is a very useful idea to take away, I think. So the idea of quantitative differentiation is that, okay, so Rademacher's theorem says Lipschitz maps, at least on Euclidean space, look linear when you zoom in at a point, at a generic point. Quantitative differentiation says actually a Lipschitz mapping looks linear at most scales. So you should kind of treat all scales the same, right? And at most scales, a Lipschitz mapping already looks linear, okay? So how do you make that precise? So I'm going to state one version of this principle, but there are a lot of different ways of doing this. But the one that we use is a result of a Zaman-Schul, which says, okay, if you have a Lipschitz mapping from Euclidean space to a metric space. Maybe for now, it's better to think of this as just Rn. Okay. And a parameter, so it's one Lipschitz, and you have this parameter epsilon. And you look at the set of all dyadic cubes in your domain on which your mapping is not close to linear with this parameter epsilon. Okay, I'll say what this means more precisely in a second. Okay, so you look at, so these are bad cubes, cubes on which your mapping is not close to linear. So then the theorem says if you add up the volumes of all of these bad cubes, then that total volume is controlled. Okay, so this is a kind of packing condition. So if you're not used to seeing theorems like this, you should imagine adding up the volumes of all the dyadic cubes that there are in the world, okay, and or inside the unit cube. And of course, when you add up the volumes of all dyadic cubes, you get one at the top scale and one at the next scale and one, and the sum badly diverges. Okay. So what this says is if you add up only the bad cubes, only the cubes on which your mapping is not close to linear, then the sum is actually controlled, which means kind of the vast majority of cubes are good. Okay. So what does epsilon close to linear mean? Well, if y is Rn, then epsilon close to linear means there's a linear map that agrees with f up to an error.
Call from Webkavina.
Sorry.
Call from Webkavina.
That's not my phone, so okay. There's a linear map that agrees with your function up to an error which is epsilon times the scale. Okay, epsilon times the side of the cube. Okay. All right, so I said you can map into a metric space, so I'm just gonna kind of brush over this. Of course, if you map into a metric space, there's no notion of linear map anymore that you can be close to. There is a way to interpret this appropriately. So this is an idea that goes back to Kirchheim, which is you kind of replace linear maps by looking at semi-norms on the domain that approximate the pullback of the distance. But let me just say that there's a way to make this idea work even for mappings into metric spaces. So this is the result of a Zusammenstuhl. So a Lipschitz map into a metric space looks linear on most cubes, and this is a very powerful idea, not just for this theorem, but in general. Okay. So how do we prove? So I want to talk a little bit about what goes into the proof of step 2 of the theorem.
Sorry, can I ask you a question about the previous statement?
Please.
Right. So how, I was just trying to picture this statement if you have, for instance, the distance function from some set, right?
Yeah.
Which would be one Lipschitz.
Mm-hmm.
Can you explain it to me how? It's like, how can that be possible? So you're saying, for instance, a cone distance from one point is going to have that estimate?
That's right. You fix epsilon.
Uh-huh.
Yeah. So right, the distance function from a cone agrees with a linear map.
Uh-huh.
Up to error epsilon on most cubes. Probably you want to avoid the cubes that contain the point or are close to the point.
Right, but I mean, what happens if I just take a cube? So you're summing, okay, so you're summing over dyadic cubes of a certain fixed scale, or you're summing over all scales?
All scales.
But then, I mean, what's wrong with the fact that, you know, the cone is a cone on any cube -1, I mean, -2, I mean, like any cube which is centered at 0 of size 2 to the power m, and I'm summing over all.
Right, so if you
that is the content, right?
If you add up the volumes of all cubes that contain the origin, that's a control. Yeah. That's a geometric series. That sum is controlled. That's exactly what's going on.
Uh-huh.
So most cubes do not contain the origin.
I'm still confused. I can go to infinity actually. So the size of the cube is actually going to.
You don't, I'm not going to infinity. I'm inside.
Okay, it's on some compact set.
Yeah, I'm inside the unit. That's yeah.
Oh, okay. You're inside. You're inside there.
Yeah.
Ah, okay, and then you're summing all of the scales. Okay. I got confused by that.
No, that's, yeah.
Okay, all right.
All right. So, okay. So this quantitative differentiation result that Camilla was asking about, this is kind of the main engine here. And so let's remember what we're trying to do. We have a Lipschitz mapping into a metric space, and we're trying to find a subset of the domain and a change of coordinates, so that when you change coordinates on the mapping and you supplement by the last, this projection to the y-axis, then you make your mapping by Lipschitz, okay? So you create a by Lipschitz mapping just by supplement, okay? And the idea is, well, okay, this set F is kind of assembled from dyadic cubes, meaning just unions and intersections of dyadic cubes. And if you try to look at any given cube as you walk down the tree of dyadic cubes, there are really three types of things that could happen. So one type is your cube just looks, on this cube, your mapping just looks not close to linear at all. I mean, there's some parameter epsilon here, which I'm ignoring, but your mapping is just far from linear. So in Camilla's example of the cone, this is a cube that contains the point of the cone. Your mapping doesn't look linear at all. But the fact is, quantitative differentiation says this happens very infrequently, okay? The total mass of these cubes is controlled. And okay, you cannot really ignore them, but there are kind of standard ways to kind of deal with these, okay? So I'm gonna ignore them for the rest of the proof, but this is a kind of a very sparse family of cubes, okay? Okay, then there are cubes where your mapping is close to a linear map, but the rank is too small. We're looking for something which is going to be by Lipschitz, so we need a rank n when we add, so that when we add m more coordinates, will be by Lipschitz. And if our rank is too small, that's going to be bad, right? If our mapping collapses the whole cube to a point, we're going to be in trouble. Okay? And the fact is, those are exactly the cubes that have small mapping content in this sense. So we're allowed to kind of throw those away. And so the remaining cubes, and the only cubes I'm going to kind of think about, are cubes where your mapping is close to a linear map of rank n, right? Or rank at least n, right? These are kind of the good cubes, okay? And I'm going to pretend that these are kind of the only cubes in the world. Okay. So let's pretend that only these good cubes happen. You're close to a linear map of rank at least n. So that means, so good cubes are cubes, you're close to a linear map of rank n. Now, the easiest scenario is if the linear map that you're close to is kind of always the projection to the x-axis, right? So every cube you look at, your mapping is kind of close to this projection downwards. Then it's very easy, right? Then you just supplement by the y coordinates, and congratulations, now you have a bi-Lipschitz map. Okay, that's a very easy scenario. Exactly, you're missing kind of the same coordinates at every scale. Okay. So slightly more difficult, but still not very difficult, is if f is always close to the same linear map, but not the one you want, right? So for example, if your mapping happens to always be close to the projection to the y-axis. On every scale you look, your mapping is close to the projection to the y-axis. That's kind of the best linear approximation for your mapping. So if you take your mapping and you supplement by y, then that's bad, because you're going to get y comma y, which is not a bi-Lipschitz map. So the idea is you just want to rotate these so they look. So this is what the role of this change of coordinates phi is. You just rotate everything, right? So somehow you apply some rotations locally so that everything now looks like a downward projection. So you kind of rotate at different scales, okay? And now you're in good shape, okay? Actually, you could just rotate the whole cube. So in this case, phi could just be a rotation. And of course, the issue is that in principle, things may switch a lot, right? So there may be some scales on which your mapping looks like one linear map, and then at 100 scales later, it may look like a completely different linear map, and then 100 scales after that, it may look like a completely different linear map. And that switching may happen arbitrarily many times, right? And this is where you kind of get into trouble. Okay. And so kind of the main thing, the main work in the proof is to control how many times this switching can happen, right? How many times your mapping can switch from being very close to the downward projection to being very close to the sideways projection at a smaller scale, right? And this is kind of what we do in the proof. And once you're able to do this, then you know that there's only kind of 10 different levels on which your mapping could be switching, okay? And then you can assemble this change of coordinates by kind of rotating at different scales. So let me try to indicate. So maybe at the top scale, your mapping is close to the downward projection. But then you pass to a slightly smaller scale and your mapping looks more like this sideways projection. Then you pass to a smaller scale, and in here, your mapping looks like a sideways. Maybe there's a downward projection. And there's some smaller cubes. So you keep kind of switching, but you're only allowed, you kind of control the number of times that this switching can happen. So it can only be 10 kind of levels of this. Then it has to stabilize. Okay. And so what your mapping phi does is you kind of want to rotate, apply different rotations at different scales, so that your mapping is actually, so that all these arrows actually point downward, right? So that the new mapping is actually well approximated by the downward projection at every scale. So at the top scale, I kind of do nothing because it's already close to the downward projection. But then this cube, I kind of rotate in place. And this cube, I kind of rotate in place. And then inside that cube, I probably have to do some smaller rotation in there to make that point downwards. And then I have to kind of maintain the, right? So if I apply different rotations at different scales, then what I get is a mapping that's well approximated by the same projection at every scale, and then it's easy to supplement. That's kind of a very vague description of what goes on in this proof. So I imagine this working like a kind of clockwork. So this is the clockwork, right? There's different rotations at different scales on top of each other. That's how you build the mapping. And I think that's where I'll stop. So thank you.
Okay, I guess we are open for questions.
So at some point, I mean, when you talked about the Kaufmann result, right? You emphasize that like it's example factors to a tree, and like, I mean, like the fact that you emphasize that, like, does that relate in any way to anything that you in your paper? Maybe like also regarding the lemma 2, which doesn't require anything about the target space.
So I mean, I emphasize the tree just because it's interesting. So you can ask, so what we asked in the paper, we actually asked this as a question. So Kaufmann's example factors through a tree, and you can ask, is this generic? So if you have one of these examples where the mapping content is actually 0. So in Kaufmann's example, the mapping content in the dimensions 2 and 1 is actually 0, right? Somehow the rank is small everywhere. Does such a mapping have to factor through a tree? And you can ask this in a kind of quantitative way as well. So, right, so is Kaufmann's example the only thing that can happen in small dimensions? And actually in higher dimensions, so in small dimensions, I think probably maybe yes. In higher dimensions, there's a lot of kind of interesting topological issues, and the answer is much more complicated, and I don't know what to say there. That's why I talked about Kaufmann.
So in your proof, the last slide, what do you mean by many scales?
So you kind of pass from the very top scale where the cube, the unit cube, and you kind of look down the dyadic scales. You keep proceeding down until you find a cube on which your mapping is not well approximated anymore by the linear map that you were using before, right? So at this cube, your mapping is well approximated by a projection and maybe by a downward projection. Maybe at the next scale, it's also well approximated by a downward projection. But eventually you come to this cube here on which your mapping looks a lot like a sideways projection. It doesn't look like the downward projection. So that's a new scale that you have to deal with, right? And what we kind of control is how many times this switching can happen. And I should mention again that this idea also appears in this kind of earlier paper of David and Stems.
I was just, hello?
Yeah.
I was just wondering if there's a generalization of this NM content to when the domain is not Euclidean.
Yeah, that's a good question. So there's certainly a definition that you could write down. So we use, I'm just gonna, sorry for the whiplash, I was just looking for the definition. So we use a definition in terms of dyadic cubes, which is kind of convenient for this purpose. You could certainly use a definition in terms of balls rather than cubes, and that at least would make sense in an arbitrary metric space. That said, a bit of a subtle issue. So if for Hausdorff measure or Hausdorff content in the Euclidean space, you can use cubes, you can use balls, you can use arbitrary sets. It doesn't really matter. It just kind of affects the constants in the definition. For this quantity, it's a little bit subtle. So if you change the definition here from cubes to using arbitrary sets in the cover, or cubes to using balls in the cover, it's not that clear how these two things are related. So we actually kind of, as a consequence of our result, prove that there's a relationship between this quantity and the quantity with arbitrary sets. But it's certainly not that simple.
Right. And is there like an analogous conjecture you can make when the domain is not Euclidean?
I'm sorry, I didn't hear you. Can you say again?
Oh, is there like an analogous conjecture you can make when the domain is not Euclidean? Because you don't have these like projection mappings, right? If the domain is not Euclidean.
I don't have a conjecture for arbitrary metric spaces. I mean, even the by Lipschitz decomposition fails for arbitrary metric spaces, as I kind of tried to show by some counter.
Right, yes. Yeah, but
so one place where I'm trying to go back to it. So one place where it might make sense to ask this question is for this setting of mapping between Carnot groups. And then there are kind of natural analog linear projections in the Carnot group setting. You could try to model the result on that. But Carnot groups are very complicated and difficult in a lot of ways. So I'm not sure how likely that is, but I think it's a good question.
right, thanks.
Can you comment on how you so you say later towards the end you said the main step is just to ensure that there are not going to be two switches when you're passing from larger to smaller scales. Can you comment on how you actually achieve that?
Right. So okay. So yeah. Let me go back to these pictures. So okay. So the main idea is this. Suppose you have suppose you're at some scale and your mapping looks like a downward projection at that scale. So up to kind of error epsilon, your mapping looks like the projection to the x-axis. And you want to show that there are kind of you can show that the cubes on which your mapping looks like a sideways projection, okay? So there could be some smaller cubes on which your mapping looks like a sideways projection. But what we show is that these cubes cannot kind of fill up the whole larger cube. So these cubes cannot be too kind of dense inside the larger cube, okay?
Mhm.
So there has to be some quantitative, I don't know, they can fill up 99% of the area, but not 100% of the area. And then this kind of iterates in a way then, and if you iterate this 10 times, you get that the cubes where the points where a lot of switching happens has a
okay.
small area.
So okay. So you're changing. So what you're really concerned is like switchings which are one inside the others, but it could perfectly be that somehow the central point of the cube is bad, but then you're kind of off-centering when you're going down.
Absolutely.
Okay, I understand.
Yeah. So certainly some points are bad. There could be
bad.
arbitrarily many switchings, but the goal is to kind of control the size of the set on which a lot of switching happens.
Okay. Good. I guess I don't see any other questions. So let us thank Guy again. Thank you for the beautiful lecture.
Thank you guys. This is great.